Exercise 133 is asking you to arrange the following compounds in order of increasing boiling point. And so we're going to follow the same sort of guidelines, the same sort of thought process as we were doing in the previous problem. We're just going to apply it to 5 molecules here. So the first thing we want to look at is which molecule has the most hydrogen bonds. So let's go through each of these and say how many hydrogen bonds each has. Now remember, to have a hydrogen bond, you need a nitrogen, oxygen, fluorine, or chlorine bonded to hydrogen in the molecule. So any molecule that does not have nitrogen, oxygen, fluorine, or chlorine will not have any hydrogen bonds. So this one here has 0 hydrogen bonds. This here has 0 hydrogen bonds. This here would have 0 hydrogen, or could form 0 hydrogen bonds to another molecule. Now, these other two have a nitrogen, oxygen, fluorine, or chlorine. The second thing you need in order to have a hydrogen bond is for that nitrogen, oxygen, fluorine, or chlorine to be directly bonded to hydrogen. And we see that that happens once here, so that is able to form one hydrogen bond to another molecule. And it happens here, so that's able to form one hydrogen bond to another molecule. Okay, so those tie. They both are able to form one hydrogen bond. Whenever they tie, you go to the next. Which molecule is able to form the most dipole-dipole interactions? Remember, to form a dipole-dipole interaction, you would need a nitrogen, oxygen, fluorine, or chlorine, just not bonded to hydrogen. So, here, any molecule that does not have nitrogen, oxygen, or fluorine, or chlorine can't form any dipole-dipole interactions with other molecules. Okay, how about our two molecules left? We have a nitrogen, oxygen, fluorine, or chlorine. Here, I'll draw these in orange. So we have our nitrogen, oxygen, fluorine, or chlorine, and it's bonded to something other than hydrogen. So that is able to form one dipole-dipole interaction with another molecule. And down here we have our nitrogen, oxygen, fluorine, or chlorine, and it's bonded to one other thing that's not hydrogen. So that also is able to form one dipole-dipole interaction with another molecule. Okay, so we're keeping tabs. They tie again. Anytime they tie, you go to the next one down on that flowchart. And so which one of these is going to have more London dispersion forces? First, let's think in terms of atoms. Does anything here have more atoms than the other thing? So let's count these up. Here I've got 1, 2, 3, 4, 5. Here I have 1, 2, 3, 4 carbons, and an oxygen. Let's include that one. Here I have 1, 2, 3, 4, 5. Here I have 1, 2, 3, 4, 5, 6, 7. And here I have 1, 2, 3, 4, 5. Okay, now I'm not numbering the hydrogens here just because that would take a long time. What you'll find is that whichever molecule has more carbons and oxygens would also have more hydrogens. And so it sort of follows the same pattern. So you can save yourself some time by just looking at the carbons and oxygens. So here, from our two that have been tying so far, that are in competition for highest boiling point, this one and this one, does one of these have more atoms? And it does. The one at the bottom has 7 that are significant, and the one at the top would have 5. So the bottom one has more atoms. And so this would be the highest boiling point, or that would have the highest boiling point. Those molecules, if you have those in a beaker, those would be sticking together through hydrogen bonds, dipole-dipole interactions, and more London dispersion forces than this other one would have, even though that other one also has hydrogen bonds, dipole-dipole interactions, and London dispersion forces. Okay, so that one at the bottom left is the highest boiling point. The next highest boiling point would be this one here, because that's the only other one that has these really strong intermolecular forces. Okay, so now we have the other three. The other three have 0 hydrogen bonds, 0 dipole-dipole interactions, so they all tie and they all bring us down here. Do any of these have more atoms than the other? Nope, they all have 5 carbons, and if you count them up, you'll see they all have the same number of hydrogens. They all have 12 hydrogens. So that one ties, and we go to the next. So it's going to be branching here that's significant. Which one has the least branching? Anytime a carbon stops going in a straight chain, so you can sort of see how this goes in a straight line. This you could imagine a straight line at the bottom up, but then there's a branch going in that one direction. And here, you have a whole bunch of branching. So you can see there's the least branching here. And if there's that little branching, then those molecules of that type will be able to line up really well. And when they line up, it gives more opportunity for London dispersion forces. So that would have more London dispersion forces and the next highest boiling point. And since this one here has less branching, it still has some branching, but it has less branching than the one in the top right, that would have the next highest boiling point. These molecules would be able to line up with each other a little better than these would, and so they would have more London dispersion forces between them, and so it would have the next highest boiling point, and the lowest boiling point would be this one. This one not only has no hydrogen bonds, no dipole-dipole interactions, but it has a lot of branching, and so the atoms that it does have are not able to line up very well, and so have very few London dispersion forces. So when you're trying to arrange things in boiling points, you would want to go through this sort of thought process to figure out which one has the stickiest intermolecular forces keeping them together. You start at the top. These are the most important. Only if it ties do you go down. Keep a little tab, and that's your reasoning for why some molecules would have higher boiling points than others.